Hello, I'm Jürgen Bellmann from SOFiSTiK, and today I want to show you our nonlinear concrete model for brick elements. We call it triple crack model because 3 cracks can occur in every element. The cracks are perpendicular to each other. We can define a smeared reinforcement in our brick elements. Of course, we can also use standard beam elements, but the smeared reinforcement can also take into account the tension stiffening effect. Here on the bottom we see the results of this smeared reinforcement, the stress in the reinforcement in the individual brick elements. But let's start with our first single span example, brick concrete ... If we look to our first analysis and make the factor to 10, we see the linear deflection and here the nonlinear cracked deflection. When we go to wind graph, we see that we have volume elements and beam elements. I now switch off the brick elements and the quad elements for the surface, and we see the beam elements. We store this view, and when we open to our animator, we can take this view settings from WindGraph and see here our rebars. So in this analysis we have real individual beam elements, but these beam elements do not know anything from the concrete stress, and so they cannot handle a tension stiffening effect. But we can also get good results in WindGraph, maybe the damage in the brick elements. We see here on the bottom the tension strain, or we see the force or stress in the beam elements and the stress in all stirrups. But let's now go to the smeared reinforcement. First on quad elements. If I here switch off the thickness, you see it is really only a quad element. Now let's double click an element and we see here the well-known distribution of the reinforcement in the cracked quad. But this reinforcement is not a real beam element, it is a smeared reinforcement because we made this input in BMS with para reinforcement AS lower side in square centimeters per meter. So a smeared reinforcement. And the same we can now also make for the brick elements. We open the new example, brick smeared crack girder. We see it is a 2-span girder, but here in this system we have not defined individual beam elements for the reinforcement, but as in BMS, for the quad elements, we can now define a reinforcement for 3D brick elements. We go into our WindGraph, look from the side, cut some elements out, make a 3-dimensional view. Let's go to the input of the reinforcement. The first reinforcement here is the longitudinal reinforcement, and we see here the value of 402. Now we concentrate on this area because this area has a width of 0.8 meters, a height of 0.14 meters. And in this area we have 7 bars with diameter 28. This is a total reinforcement of 43 square centimeters. So this reinforcement relative to this small area gives a value of 402 square centimeters per square meter. And this is the value that we have to define for these elements as a smeared reinforcement in X direction. The same we can do for all other brick elements. You see, you have to make a good group division for your section so that you are able to give a smeared reinforcement for every group you need. We now can get more results in WinGraph. That is here the nonlinear results for volume elements. We see here the stress in the reinforcement directly. Second, third stress. We can get concrete stresses, maybe the compression stress in the concrete or the tensile stress. Here we have a pure concrete tensile stress in the center, but below, after the crack opening, the stress falls down to 0. And we can get here the crack directions directly. If we now look to the total result from the side, we see here the cracks in midspan and here over the middle support. Now let's have a look to the manual to see all features. We use the ladder material. In the other output you will find this curve. We see here the tension side and here a compression for the stress state that the stress in Z direction is 0. Here this value is the uniaxial stress that here in this example is minus 38 Newton per square millimeter if you only load your specimen only in X direction. Now to the most important new implementation of the ladder material. If we look to a specimen that we only load vertically and now increase a horizontal stress, then we have here the linear behavior. In the linear behavior we have a Poisson ratio 0.2. But now we increase the stress. We go to this picture, the first crack comes. And if we now increase the horizontal deformation, we only pull the two pieces a little bit to the side, and this crack opening has no effect now on the vertical stress. That means the horizontal deformation has no effect on the vertical behavior, and that means mu is 0. And this is the big advantage we implemented in the triple crack model, that after a crack we do not take into account the Poisson ratio anymore. That was the example BRIC smeared crack, and there is also a nice example volume meshing video where I used this new smeared reinforcement. We see here a foundation of a wind turbine, and also here now we can watch design volume elements, the stress and the reinforcement, here in the tangential direction, and reinforcement 1 is the radial reinforcement and reinforcement 3 is the vertical reinforcement. How to input you can look in the example file. Maximum crack strain now is really the strain in the crack. This maximum crack strain, if we go to the manual, is just this strain that is above this peak of the FCTK curve. So we really only see elements that are really cracked. One comment to the used ladder material law. There's also a nice file, plot.dat, where you can really look to the surface of your yielding. We have here the three-dimensional view, and these axes are very important. If we now only increase the stress in this direction, we have here a point where the axis goes through the surface. And this is just the uniaxial strength of the material. So, thanks for listening and goodbye.